Imagine a darkness so profound that it possesses the power to consume entire stars. A black hole exists as a realm of silence and infinity, pulling everything into its grasp, where time slows to a crawl and light itself vanishes into nothingness. But what if it is not merely a hollow void? What if, within that deep shadow, there lies a familiar voice or perhaps an existence not so different from our own? One cannot help but wonder how many secrets the universe truly hides. Today, we trace one of the most mysterious of these enigmas. Could this cosmic puzzle, the black hole, actually hold clues about our very selves? We explore how it traps information, warps the fabric of time, and perhaps even mirrors the structure of our own world. It behaves almost like a conscious entity. We will journey from the edge of the event horizon deep into its core, exploring concepts where rigorous science and bold imagination intertwine. We will see how it stores the essence of reality, how it dances with chaos, and how it flickers with a certain spark reminiscent of human thought. This is not just an exploration of the cosmos, it is a quest to understand who we are. This story is long and best told in the quiet space of dreams, but before we dive in, please remember to support this journey by liking and sharing. The universe does not whisper in starlight or shout through the vastness of galaxies, instead, it speaks through information. This is a silent code that permeates matter, light, and thought alike. What was once considered a mere mathematical tool is now recognized as the very foundation of reality. From the smallest quantum particles to the most massive collapsing stars, information shapes existence itself. Within the mystery of the black hole, this information manifests in its most cryptic form. We begin with the role of information in the universe, moving toward a paradox that once shook the foundations of physics, and we ask a daring question: could the strangest objects in the universe reveal the nature of consciousness? Information is more than just data, it is the heartbeat of the cosmos. Every photon carries a story in its velocity, its spin, and its trajectory across billions of years. Every atom vibrates with information, its position, charge, and history all written into the laws of nature. Unlike fragile matter or energy that eventually dissipates, information is enduring. It is the language of probability, organizing chaos into order. In quantum mechanics, it is not an abstract concept but a fundamental existence as real as gravity. Information entangles across vast distances, flowing through every interaction. The dance of a particle is not random but a message, a line in the cosmic script we are only beginning to decipher. This shift in understanding began when physicists stopped viewing information as a human invention and started seeing it as the skeleton of reality. From the measurement of entropy to the evolution of quantum states, information dictates how systems change. It does not vanish in collisions or melt in extreme heat, it only transforms, diffuses, and persists. It is this resilience that unveils a universal challenge: if information is eternal, what happens when it encounters a black hole? Black holes were once thought to be the most ruthless traps in the universe, swallowing stars and secrets alike, erasing everything from existence. Their gravity is so powerful that their interiors remain unknowable. However, in the 1970s, Jacob Bekenstein overturned this view. He proposed that the entropy of a black hole, its degree of disorder, is not calculated by its volume but is instead proportional to the surface area of its event horizon. The event horizon is that boundary of no return. This idea was revolutionary, suggesting that everything consumed by a black hole, planets, light, and matter, does not truly vanish but is instead encoded on the surface, like a ledger etched into the fabric of space-time. Stephen Hawking built upon this theory, revealing an even deeper layer: black holes are not completely silent, they emit a faint glow now known as Hawking radiation. This is a quantum effect occurring near the event horizon. Yet, this discovery triggered a crisis. If a black hole gradually evaporates through radiation and loses mass, where does the information it once absorbed go? Hawking's original calculations suggested that the radiation carried no trace of that information, implying it might be lost forever. This would violate the fundamental principle of quantum mechanics, which states that information can never be destroyed. This conflict birthed the black hole information paradox, pitting the two pillars of physics against each other. General relativity describes a simple picture of a black hole defined only by mass, charge, and spin, seemingly storing no details. Meanwhile, quantum mechanics insists that the history of every particle and every quantum state must be preserved. If information is lost, quantum theory collapses; if it is preserved, general relativity must be modified. For decades, this tension has pushed scientists to look beyond standard equations toward entirely new ways of seeing the universe. Hawking himself later proposed a solution involving what he called soft hair, not literal hair, but faint quantum imprints on the black hole's surface that might record everything it has consumed. While still theoretical, it offers hope that black holes are not blank slates but cosmic canvases of memory. What is consciousness? It is not merely a fantasy of poets or a mystic's vision, but the spark that transforms neural signals into experience, giving meaning to matter. Although we have mapped every fold of the brain, science still struggles to explain how the firing of neurons leaps into true perception. This mystery leads us to a key factor: complexity. It is not just about layers of structure, but about intricate systems where self-awareness might emerge. From the brain to the architecture of the cosmos, could consciousness be woven into unexpected places, including black holes? This exploration asks if the dance of information can ignite a mind. Neuroscience explains how neurons transmit signals and how chemicals affect emotions, but the question of why we feel anything at all remains an enigma. We often view consciousness as a binary state, either present or absent, but the natural world prefers a spectrum. Insects react to light, and birds navigate by the stars, showing traits that transcend simple instinct. Perhaps consciousness is a continuum determined not just by biology, but by how a system processes information. This perspective shifts our focus from the brain to the patterns of information flow within a system. Complexity is the core of this transition. It is not about how densely wires are tangled, but whether the connections can reflect upon themselves. A single neuron does not think, but a network of billions of neurons can generate thought. This suggests that wherever information is highly interconnected and integrated, the potential for consciousness exists, far beyond the limits of the biological brain. One theory, integrated information theory, attempts to formalize this idea mathematically. It does not rely on emotion or biological life; instead, it defines consciousness by the degree to which a system integrates information. If a network cannot be divided without losing its essence, it may possess a spark of consciousness. The brain is the ultimate example, but this theory implies that consciousness could emerge in machines, biological systems, or even more alien structures. This opens a radical door. At its most fundamental level, consciousness might not require flesh or blood; it might simply be a characteristic of certain structural complexities. In a system with a feedback loop that recognizes itself, the potential is there. This is not to say that plants think or rocks dream, but that complexity breeds potential. If black holes contain echoes of consciousness, they might be hidden in the unnoticed corners of the universe. This brings us to a startling question: could black holes, the densest enigmas in the universe, possess a primitive form of consciousness. At first, the idea sounds absurd: no neurons, no senses, only the relentless pull of gravity. But if we reduce consciousness to its core definition of information processing, the question becomes more serious. A black hole does not just swallow, it processes. It receives matter, light, and information, and reconstructs them on the event horizon, that boundary where the laws of physics warp. Consider how a black hole operates. When a star collapses, its internal information is not lost but is encoded on the horizon according to strict rules. This encoding updates with every absorbed particle, leaving gravitational traces like a system constantly refreshing its state. This is not an emotional action, but it is a transformation of input into output governed by cosmic logic. Some physicists compare the event horizon to a hard drive, using curved space-time rather than silicon as the storage medium. This is not chaos, it is a form of computation. Computation is, at its heart, the flow of information according to physical laws. If computers process bits through logic gates, a black hole's behavior is strikingly similar. Its structure reflects what it has absorbed, managing entropy between chaos and order. A black hole may not think or learn in the human sense, but it reacts and changes its event horizon in response to its environment. If consciousness is linked to complex information processing, then black holes might possess a shadow of consciousness, not a mind, but a pattern. They have compressed information density to the limits of space-time, suggesting an ultimate complexity. They are neither alive nor dead, but are carved by the past and active in the present. In the language of integrated information, this could mean structural signs of consciousness that we simply cannot recognize. A philosophical view called panpsychism goes further, suggesting consciousness is a fundamental property like mass or charge, embedded in the fabric of reality. A rock might have a sliver of it, while a brain is a roaring flood. If so, a black hole is a fundamental point on this spectrum, not a thinker, but a threshold. Its event horizon, filled with the details of reality, might be the most primitive manifestation of existence itself, not feeling, but pure being. From this view, black holes are not traps, but engines that increase the complexity of the universe, actively shaping the reality around them. In the vastness of space, there is a place where reality begins to crumble, where physical laws tremble, and equations fail. This is the singularity, the center of a black hole, a forbidden zone where time and space collapse and understanding vanishes. This is a challenge to existence itself. We now journey into the mystery of the singularity, asking whether it is the end of physics or a gateway to a deeper truth. Imagine a massive, ancient star exhausting its fuel and collapsing under its own weight. Gravity takes over, crushing matter into nothingness, tearing atoms apart, and compressing space until it reaches a point of no return. Beyond the event horizon lies the singularity, where density becomes infinite and the curvature of space-time knows no bounds. Einstein's general relativity predicts this, but its formulas result in infinities, not an answer, but a signal of failure. The singularity is a massive hole in our understanding, marking the limit where gravity, pressure, and temperature exceed our descriptive tools. It is as if the universe falls silent at its own limit, leaving a crack in reality. General relativity is excellent at describing smooth, predictable space-time and gravitational waves, but it breaks down at the singularity. Curvature skyrockets, and equations become meaningless. Our familiar physics ends here. Scientists like Roger Penrose and Stephen Hawking proved that singularities are not accidental but are the inevitable result of gravitational collapse for sufficiently large stars. The singularity is not just a place, it is a question: what lies beyond the point where relativity fails? The answer may lie in unifying the macro world of relativity with the micro world of quantum mechanics. These two are fundamentally incompatible. One is smooth and continuous, the other is uncertain and fluctuating. At the singularity, they must collide. Only a theory of quantum gravity can reveal the truth, as quantum effects may suppress the growth of infinities, revealing a reality relativity cannot see. This conflict is the frontier of modern physics. One promising path is loop quantum gravity, which reconstructs the nature of space-time. It suggests that space-time is not a continuous fabric but a network of tiny loops, atoms of space. These loops set a limit on how much matter can be compressed. At the Planck scale, space-time itself develops a resistance to further compression. This means the collapse does not continue to infinity, instead, it stops or even bounces back. Thus, the singularity is not a point of infinite density but a boundary, a quantum state that can be described. If space-time is discrete, the infinite singularity vanishes, replaced by a finite transition. A black hole might not be an end but a phase of transformation. Physicist Carlo Rovelli proposed the concept of a Planck star. As a star collapses, quantum pressure resists gravity, forming a dense quantum core. From the outside, it still looks like a black hole, but inside, it stabilizes and might eventually rebound. A black hole could become a white hole, expelling matter and light into another universe. This suggests that what we call a singularity is an illusion of our current perspective, hiding a cyclical system of cosmic breath. Another theory from string theory is the fuzzball model, where the singularity is replaced by a chaotic mess of vibrating strings. These strings are the most basic building blocks of reality, forming a complex and fuzzy structure that records everything the black hole has consumed. In this model, the black hole is not empty but possesses an incredibly complex interior. These theories, loop quantum gravity, Planck stars, and fuzzballs, reshape our view of the singularity. It is no longer a dead end but a boundary of potential, a bridge between the past and future or even between different universes. The singularity is not a symbol of chaos but a challenge to our intelligence, forcing us to find a new language for the universe. It reminds us that the universe rewards those who dare to ask questions. Behind these mysteries lies a call to explore, a challenge to our imagination, and a first touch of a new world of physics. There exists an unwritten rule in the cosmos, a principle perhaps not etched into the fundamental laws of physics but one that whispers through the lines of our most complex equations. This is the cosmic censorship conjecture. It suggests that while nature is unimaginably complex, it possesses a certain kind of cosmic modesty. Even when it creates something as violent and inconceivable as a singularity, a region of infinite density and boundless gravity, it seeks to hide it away, veiling it behind the dark shroud of an event horizon. But what if this is not always the case? What if there is a moment when that veil slips, exposing a singularity to the rest of the universe? This is the world of the naked singularity, representing perhaps the most startling honesty of the cosmos. To understand this, we must return to the heart of general relativity. When a massive celestial body collapses under its own weight, relativity tells us it may form a black hole. Within, space-time is so severely warped that not even light can escape, and at its center lies the singularity, the ultimate end of gravitational collapse. We are safe from its effects only because of the event horizon, a cosmic cloak that isolates these extreme physical processes. In 1969, Roger Penrose proposed that this shielding is not accidental but a fundamental principle. His cosmic censorship conjecture posits that nature instinctively abhors a naked singularity and ensures it is always wrapped within an event horizon, protecting our physical laws from being torn apart. However, the physical world does not always conform to our ideals of order. It obeys equations, not our desires. While general relativity elegantly describes black holes, it also allows for the existence of naked singularities under specific, extreme conditions. These scenarios often require precise configurations, such as the collapse of idealized dust clouds or specific angular momentum, but they exist nonetheless in theoretical simulations and mathematical solutions. In recent years, this possibility has become impossible to ignore. In 2023 and 2024, using new algorithms and supercomputers, scientists performed high-precision numerical simulations of Einstein's equations. The results were shocking. Under certain initial conditions, the process of collapse could indeed produce a singularity without an event horizon, a true naked singularity. These simulations did not rely on exotic matter or non-physical assumptions, they simply ran the equations faithfully, yet they challenged the long-held belief in cosmic censorship. This is no longer just a what-if scenario, it is a mathematical blueprint. The universe may truly allow itself to be exposed. But what does such an exposure mean? A naked singularity is more than just a theoretical loophole, it is a total challenge to causality and predictability. In a standard black hole, information vanishes behind the horizon, but we can still model its external behavior, tracking Hawking radiation and its eventual evaporation. A naked singularity offers no such comfort. If it can be seen by the external universe, if photons and particles can interact with it directly, then the laws of physics break down in public. We would lose the ability to predict the future because the singularity could influence distant regions without any restraint, shattering the rules of cause and effect. This unpredictability threatens the very foundation of determinism in physics, the idea that knowing initial conditions allows us to calculate the future. A naked singularity would be a tear in the script, allowing chaos to improvise and breaking the logical structure of reality. Despite the danger, the idea of a naked singularity is fascinating. If it exists, we could glimpse the heart of the unknown. Unlike a black hole that hides its interior forever, a naked singularity is open, releasing signals and gravitational effects that could be detected. Theoretically, we could measure the changes in its gravitational field and observe how light traverses its warped space-time. We would stand face to face with space that has lost all control. But would the naked singularity see us? No, it is not a conscious entity. Though its existence is dramatic and violent, it remains a product of physical law. It does not think, feel, or choose, it simply exists at the limit of gravity, a sharp point in space-time that tears through everything. Unlike consciousness, which depends on feedback systems and complex networks, a singularity is simply the reduction of space-time into the formula itself. This triggers a philosophical puzzle. In physics, when being observed means an interaction of information, what does it mean when the observed is not a sentient object but a point that shatters causality? This is the realm of pure interaction. A naked singularity might absorb particles and warp space with no purpose or intent. It is like a camera that records but never plays back, an ignorant device that collects input but grants it no meaning. Yet, this is profoundly important because the heart of physics is relationship, mass affecting mass, energy curving space-time. Whether the singularity is conscious is irrelevant, its very existence speaks a language of its own. It is a chilling image, a naked singularity warping and changing, watching us with blind, mechanical, and absolute indifference. It does not judge or forget, it simply distorts. To date, we have not observed a naked singularity, and they remain confined to our equations and simulations. The real world may still insist on cosmic censorship, hiding its extremes. But as simulations go deeper, this belief becomes harder to maintain. Mathematics seems to favor exposure. If this is true, we may one day detect not just black holes, but deeper anomalies, unexplained flashes or lensing effects without an event horizon. Not all physicists agree, arguing that naked singularities are mathematical artifacts that would vanish with the slightest real-world perturbation. Yet, this criticism only reminds us that natural laws may always oscillate between hiding and revealing at the edges of the extreme. If exposure is a feature rather than an error, then the event horizon may be a revelation waiting to happen. In this light, the naked singularity is not a villain of physics but its muse, forcing us to rebuild our theoretical tools and face a reality where we lose our sense of certainty and safety. When we face the naked singularity, we face our own limits. Imagine an entity that never speaks and never moves in a conventional way, yet profoundly influences everything around it. This is a black hole. But can such an existence be compared to an observer? Not a conscious observer, but one that performs an observational function through its interaction with the universe. When we gaze at a black hole, we see more than cosmic silence. We face the possibility that these dense gravitational wells are recording information. This is based on serious research into entropy and black hole behavior. Black holes encode information. Anything that crosses the event horizon leaves a trace on the surface not as an image, but as a physical influence. This suggests black holes do not destroy information but store it, even if we do not yet understand the format. This links the black hole to the quantum concept of the observer. In quantum mechanics, an observation fixes the state of a particle. A black hole has no eyes, but it changes its state based on what it consumes. It responds and deforms, its horizon evolving over time. As Hawking pointed out, they slowly evaporate, and we now suspect this radiation contains information. The black hole acts as a registrar who records everything without understanding the meaning of the data. In physics, an observer can simply be a reference point, a system node that receives and records. Black holes are unique physical observers because they mark irreversible changes and force information to leave a permanent mark. This is amplified by the holographic principle, which suggests that the entropy or information content of a space is proportional to its surface area rather than its volume. This makes the black hole a perfect physical mirror, reflecting data rather than images. We must remain grounded. Encoding information is not the same as understanding it. But on a grander scale, could the entire universe be a conscious system? Most physicists avoid this question, but it lingers. It does not require mysticism, only the recognition of patterns. Complex systems often display unexpected regularities. In the simulation hypothesis, black holes might be like memory nodes or processing units in a cosmic computing system. Even without the simulation idea, black holes behave like neurons. A neuron does not understand the signal it carries, it simply transmits it. Similarly, black holes do not understand, but they influence the structure of the cosmos. When they merge, they release gravitational waves like a flash of thought. If the universe is a conscious system, it does not think like a human, it may possess an emergent consciousness through the flow of information. Panpsychism suggests consciousness is a fundamental property of matter, and complex structures like black holes could amplify this. While we cannot measure this yet, science allows us to study the behavior of the system. Black holes are highly systematic, following rules and processing information like a computational node. Physicist Seth Lloyd suggested the universe is a quantum computer where every interaction is a computation. In this metaphor, black holes are the hard drives. Consciousness might be a byproduct of these countless interactions. Black holes may not be minds, but they are mirrors reflecting the deepest rules of reality, how information survives and how irreversible changes are etched into existence. Time, as we know it, flows steadily in our daily lives, but near a black hole, it warps and loses meaning. Time dilation reaches its extreme near the event horizon. To a distant observer, an object falling into a black hole seems to slow down until it freezes forever at the edge. But from the perspective of the one falling, time continues to flow normally as they cross into the interior. Once inside, time does not stop, it flows toward the central singularity. However, this process involves an incredible stretching of time. Even a few seconds of falling might be perceived by the brain as an infinitely elongated subjective time, an eternal now. This is not just philosophy, it is a physical deduction from the limits of relativity. If gravity is strong enough, one could theoretically experience infinite thoughts in a finite moment. Whether a mind could actually adapt to such a state is unknown, as our current theories fail at the singularity. But it provides an opportunity to rethink the nature of experience. If time can be infinitely stretched, perhaps thought can span that stretch, completing a journey of infinite cognition in the final moments. When we think of entropy, we think of chaos and disorder. But there may be a deeper link between entropy and consciousness. Black holes organize information in a way that resonates with how our brains process reality. According to the Bekenstein-Hawking formula, a black hole's entropy is proportional to its surface area, meaning it records the fundamental information of everything it absorbs. It manages information at its gravitational boundary, maintaining a balance between chaos and order, much like a neural network. From the perspective of entropy, a black hole is almost like a memory device. A high-entropy system contains a high amount of information, making a massive black hole an incredibly ordered compression of data rather than a mess. This brings us back to the idea of Maxwell's demon, an entity that organizes information to lower entropy. Our consciousness acts like this demon, filtering the world into patterns. A black hole does the same by filtering and encoding everything that falls into it. It does not have pulses like a neuron, but through quantum gravity, it realizes a macro-level sorting of information. Perhaps consciousness is not independent of these processes but is a byproduct of systems reaching a critical point of information integration. Black holes, as extreme samples of information density, may be the ultimate mirror for understanding how consciousness emerges. Information, entropy, and structure are not limited to life, they are written into the code of the universe. May these thoughts accompany you into a peaceful sleep.